Here on number 9, we have another titration. So if we just want to know the molarity or the amount at the equivalence point, we do what we did on number 8, either A or B, thinking about the moles being equal. 9, 10, 11, the next few are about all the different places along a titration curve that we could want to know about our chemicals or we could want to know about our pH. So in this case, we have in our flask or beaker a base. That means we start with a very high pH because we have a high concentration of hydroxide. As we add our acid, that pH drops. We'd have a rapid drop at the equivalence point, and then it would end low, and we could find molarities. We could find lots of different things doing this, or the amount of volume, etc. So here it asks, well, what's just the initial pH? So that's a great, easy question here. We've got a strong base in solution. What's the pH? Here, it is important to remember that the calcium hydroxide, there is 2 hydroxides per formula. So that 0.15 gets multiplied by 2, 0.015, so it becomes 0.03 molar. If I know the hydroxide ion concentration, I can find the hydronium or hydrogen ion, whatever you prefer. So we have a lot of base, very little acid. We do the negative log of that, and that gets us our pH. So in this case, we have a very high pH, just like we predicted before we do any of our titration. On part B, we start doing some stoichiometry, but we're not necessarily at the equivalence point. Here, it's limiting excess. The whole process of an acid-base titration is limiting excess. It is, in this case, we would have an excess of our hydroxide until we get to our equivalence point. Then they are equal to one another. Then we start having an excess of the HCl. By looking just at this number, I don't know by looking at it what I would have an excess of. I could guess and make a prediction as to whether the pH is high or low, but really the math would also prove that. So if I wanted to make a prediction, I would recognize that this is 0.015, this is 0.01. So my base is more concentrated than my acid. My base has 2 hydroxides for every 1. So really, this is like it's 0.03, this is like it's 0.1. So I have way more hydroxide than hydrogen ion, 20 mils of this. So even though I've added 30 mils of this, I probably am still at a basic pH. So we'll go through the math and that will support that as well. So the start is the same. We know the molarity of that, but we also want to think about, well, how many moles of hydroxide were there? Then we do kind of the same thing with the hydrochloric acid. We know its molarity, or we know how many hydrogen ions are there. When I take that molarity times the volume, I know how many moles of hydrogen. So I know my moles of hydroxide, I know my moles of hydrogen, and I was right that I still have more hydroxide than hydrogen. So I want to figure out how much of my excess is still there. In this case, the hydroxide is the excess. So I have to think about, well, I had a certain number of moles and some moles went away. I am subtracting. This is limiting excess. How much is still there? So I still have 0.0003 moles that are in solution. We can't just do this with molarities because we are mixing liquids and as a result, increasing or changing our volume. So what we've done here is the new volume of the solution, 20 milliliters of base, 30 milliliters of acid. We now have 50 milliliters of liquid. In the problem, it would probably use a phrase like assume volumes are additive because there's some other little tricky things here that may not make that totally true. We have to make the math easy enough that it's possible. But now I'm thinking, well, how much hydroxide is still in solution? How much solution do I have at this point? So I still have a molarity of hydroxide, but that's quite a bit lower. Some of it has gone away, and I have watered it down, or I have more total solution. So then I plug that in here. I know my hydroxide, which allows me to find my hydronium. My hydronium is still a fairly small number. In a titration, the pH stays high until we have that rapid drop-off. So we aren't at that rapid drop-off yet. So we're not gradually going down. We still have quite a big excess of hydroxide compared to hydrogen. So that makes sense that our pH is still quite high. Not as high as we started, but in that 11 to 12 range makes a lot of sense. This is some of the more challenging math that we could do here. It would likely be broken down maybe into 1 to 2 steps. You might see some of this on some practice problems, on some online homework. On an AP question, it would likely not be all the way through this, but maybe just the limiting excess part, maybe an estimating the pH part, or maybe a multi-part question if they want you to do all of that at once.